the divergence and the integral tests and other tests. So we talked about sequences and series. So the difference between a series and a sequence is that when we are dealing with a sequence, we are talking about just numbers that come in consecutively, like 1, 2, 3, 4, 5, 6, 7, 8, so forth. That's a sequence. A sequence converging, meaning that after a while, the numbers start to be very close to one another. And if we carry this sequence on to infinity, then they tend to be closer and closer to a particular point, so that the definition of the limit was basically with the epsilon delta. A series, on the other hand, is a sum of some sequence. So we take a number sequence where the numbers keep coming and we add them all together. And a series converging is treated basically, well, you can treat it in one of two ways. One, just treat it as the sum and look at the sum, how it behaves as more and more stuff is being added. Or look at it in terms of take a part of that sum, let's say k first elements, look at that sum and then just let that go to infinity, the k go to infinity, and see what happens to that sequence of the subsums. Well, we talked about ways of determining whether a series or a sequence converges, and now we're going to talk about the series convergence. So we always talk about the sums in this particular instance. So when we're talking about, there are some tests that I'm going to go through. The divergence test is fairly simple. So because we keep adding things, an, we add the next one and the next one and the next one and so forth. So unless the stuff that we keep adding into our sum, unless that goes towards 0, it's not possible for the sum to converge. Obviously, if we keep adding, let's say a number, any number, let's say 0.2, and we keep adding that enough, then it goes to infinity, right? So for the series to converge, these terms that we add must approach 0. It's not a sufficient condition, but it is a necessary condition. Necessary meaning if they don't go to 0, it will not converge. It's not going to always converge if they do go to 0, but that's another issue. So a very simple test called the divergence test is we look at the terms in that sum. Do they approach 0? If they don't, then the series diverges. Very simple. We talked about this already. Also, we talked about the integral test. Well, basically, the integral test's idea is fairly simple. We can approximate the sum using the integral, and we already talked about this as well. So the integral can give us both the upper and the lower limit for the partial sums, and then, you know, as this k up to which we sum these values goes to infinity, the integral's limits will give us upper and lower limits. And it's fairly simple. This particular integral, when we start here at 1, then this particular integral gives us the lower limit. Here was an example. This particular integral gives us the upper limit of that sum. So in reality, when we look at this, we actually already mentioned this, is that one way to test is that if we have a sum as n ranges from 1 to infinity, and then the integral of f of x, t of x is from n, and this n is now some number to infinity, some number large enough so that the positive integer such that everywhere everywhere after values larger than this n, f is continuous, decreasing, and f of n is equal to a of n for all integers. Then one or both, I mean, if one of these converges, both of these converge, and if one of these diverges, diverges, then both of these diverge. So if the question is does this sum converge, you can look at this integral, and if that integral does converge, then the sum converges as well. We'll look into this a little bit more closely later. What this integral to infinity is. I promised I will do this. Here were examples of using the integral test, so you can try this out. Then there was this thing called the P series. So these are subharmonic or superharmonic or harmonic series. The harmonic series being 1 over n, and superharmonic series or P series with P greater than 1. It's 1 over n to the P, where P is greater than 1. If P is smaller than or equal to 1, then this will diverge. And if P is greater than or equal to 1, greater than 1, then this will converge. And we can do this test by using the integral test. So the integral test easily gives us this result. Not going to go the way we talked about this last time, so not going to do this a little bit more. Here was a question about estimation. So the integrals, in fact, give us a pretty nice way of estimating what the actual sum is, because if we take the sum up to some finite number n, and then take the integral that corresponds to the sum from n plus 1, we get a lower approximation. And if we take the sum up to this Sn and we take the integral from that n number n, we get an upper limit. So actually these limits are they squeeze it pretty tight, this sum. So for many functions, we can get a pretty nice approximation of the function, of the limit using this f of x, where f of x is pretty much the same as this a of n for all of the n's. Well, it's equal to those, but then between those integers, as long as it's decreasing, it works. This was not proven, I think, but yeah, it's a little bit out of scope for this to be able to prove this, but it's a nice result. Okay, not going to do this remainder estimation, so I'm not going to ask that of you, but the integral test is something that you should be able to do. Okay, so that gives us 3 ways of checking whether this whether a series converges: the integral test and then the convergence test. The integral test is pretty powerful. Well, another thing, very often the case is we know a certain particular sum converges or diverges, then we can often come up with a test where we approximate upwards or downwards, depending on whether we are establishing divergence or convergence. And this so-called comparison test is a way to determine convergence or divergence of a series. So for instance, if we have the sum of 1 over n squared plus 1. So this is not quite the same as the series of sum of 1 over n squared, but the terms are all positive, obviously. We can look at these sums, all these are positive, so these are increasing sequences. So as we take longer and longer partial sums up to some limit, then whatever we get will be an increasing sequence. On the other hand, we see that every term in the first sum, in this 1 over n squared plus 1, is strictly smaller than a term in this second sum, which is 1 over n squared. So every partial sum of this first one is smaller than every partial sum of the second one, which is then, of course, smaller than this sum of that we take up to infinity of this 1 over n squared. So we can then conclude that whatever this sum is, the limit must be smaller than the limit of this second series. So this 1 over n squared plus 1 must be smaller than or equal to the sum of 1 over n squared. Obviously, because we're adding smaller things together, and both of them are being added as an infinite sequence. So, yeah, the series will converge if we are adding smaller things. Similarly, on the other direction, if we have 1 over n minus 1/2, let's say, which is being added, and we look at the series of 1 over n, which we know to diverge, and every term in the first series is then larger than every term in the second series. So we know that because the 1 over n series diverges, then this 1 over n minus 1/2 series will also diverge, because we are adding things that are bigger, and this 1 over n sequence goes to infinity, and we're adding things that are bigger than this 1 over n, then obviously this 1 over n minus 1/2 will go towards infinity. Fairly simple thing. So whenever we are going to be comparing these things, here's the comparison test. If we have an is smaller than or equal to bn for all of these n from some point onwards, then if this B sequence converges, this B series converges, then this A series also converges. And on the other hand, if A is larger than or equal to this A sequence terms are larger than this B sequence terms, and the B sequence diverges, then the A sequence diverges as well. So the proof is relatively simple. You can check out the first part of this proof. It's fairly easy to see that if you are adding things, then the partial sums will always be smaller, so it's going to have a limit. All right, how to use this? Fairly simple. For instance, we have this one, let's take this first example, this A. We have this 1 over n to the 3 plus 3n plus 1. And we compare it to this 1 over n to the 3. So 1 over n to the 3 plus 3n plus 1 is strictly smaller than 1 over n to the 3. So we know that this series is going to converge, because this 1 over n to the 3 will converge as well. And let's take a look at that C. We have this 1 over logarithm of n. Well, we know that the logarithm of n is going to be smaller than n. So 1 over the logarithm of n is going to be greater than 1 over n. And because the 1 over n sequence diverges, then 1 over the logarithm of n sequence diverges. So there you have it. Well, here's a thought. Use the comparison test to determine if this series converges or diverges. Were I you, I'd do it in 2 stages. Just find the one that you compare it to. So let's do a group work here at this stage. I'm going to pause the recording. Okay, welcome back. So, can I hear some ideas? What was the thing that you should compare this to? Or what would you be able to compare it to determine that this in fact does converge? Anyone? Well, let's look at it. So each of these terms is of the form n over, and we have n to the 3 plus n plus 1. Okay? So first of all, notice that we can now take this to be, this is definitely smaller than or equal to, because the divisor or the denominator here contains n to the 3 plus n plus 1. So if we make the denominator smaller, then we make this this quotient bigger. So this has an upper approximation at n to the 3 plus n, right? So whatever that is going to be smaller than this because n is going to be positive. And then this is, in fact, we can write this as 1 over n to the 2 plus 1, which is smaller than 1 over n squared, and sum over 1 over n. So this is what we can determine, right? We can determine that this converges, so we're good. So this is a fairly simple task, and I would expect you guys to be able to do this comparison. If you are faced with a sum over some kind of terms, and then this term, you can approximate it and find something that is guaranteed to converge, then you should be fine. I mean, you can do this with the integral test, but the integral test will give you, it'll be relatively hard, a hard task to do. Okay, moving on. The comparison test works nicely if we can find a nice comparable series, but sometimes it can be difficult. For instance, if we have this series where n, now it starts from 2 because we have 1 over n squared minus 1. If we can start from 1 because it would be 0 there, the divisor, so yeah. We might want to compare it to 1 over n squared, but this comparison doesn't work because 1 over n squared minus 1 is actually greater than 1 over n squared. So comparison doesn't help us directly here. Well, one way to do this is to use what is called the limit comparison test. So one way to do this is to look at the quotient. If we have two sums, two series, one is the A series and one is the B series, sum over AN and sum over BN. And these terms are positive, so no zeros allowed. And if we look at the limit of the ratio of AN and BN, and that ratio approaches some limit that is not 0, then for sufficiently large n, AN is roughly that ratio times BN. So either both series converge or both series diverge, because then it'll be roughly just looking at the AN, BN series and AN series being L times the BN series, which we know is to converge. But of course, this limit needs to be not 0, obviously. Also when we do this approximation, there's a little bit of a hand waving here in this justification. So this is not actually a proof of any sort. But let's look at what this test, or this ratio test, or this limit comparison test gives us. If we look at the ratio of the terms in the first series, 1 over n squared minus 1, to the terms in the second series, 1 over n squared, and we notice that their ratio goes towards 1 as n goes to infinity. And here we conclude that the ratio, the series of 1 over n squared minus 1 also goes towards infinity. And there's another way to prove this one. another way to prove this one, and that is to kind of like a change of variable, if you will. So let me just say here one way to do this, to revert to comparison test in this case. And if we have this 1 over n squared minus 1, right? And that can be written as 1 over n minus 1 times n plus 1, right? And this is for n greater than 1, so from 2 onwards. This is in fact, we have a, in the denominator, we have n minus 1 times n plus 1, something times something, and n plus 1 is greater than n minus 1, both being positive. So if we replace this by something smaller, so we get greater, so that this is greater than, sorry, smaller than 1 over n minus 1 squared, right? And let m be n minus 1, then sum n from 2 to infinity 1 over n squared minus 1, then that's smaller than sum n from 2 to infinity 1 over n minus 1 squared. Which can be written as sum as, and now m ranges from 1 to infinity because m is n minus 1, 1 over m squared. Not infinity, but you see we shifted it a little bit and we get 1 over m squared, and we know that this, which converges. So this is another trick that we can do because the sum ranges from 2 onwards, so we can shift it to the left. But the limit ratio works pretty well as well. So what if this limit is 0? An over bn is 0. Well, in this case, the sequence an over bn is a bounded sequence. And as a result, we can write that an is smaller than m times bn from some point onwards. So if bn converges, then an converges. And on the other hand, if an over bn goes to infinity, then if b diverges, then an diverges as well. So this can be compared in 3 ways. Here is the summary. If the limit is, if we have a sequence, A sequence and B sequence, and suppose one of them is known, let's say B sequence's convergence or divergence is known. And if the ratio is, the limit of the ratio is some fixed number, not 0, then they are equiconvergent. So that if one converges, both converge, or if one diverges, both diverge. On the other hand, if they are, if their limit is 0, then the convergence of B implies the convergence of A, but A may converge regardless of what happens to B. On the other hand, if the ratio is infinite, then if B diverges, A must diverge also, but if B converges, we can deduce nothing about the convergence of A. So this is basically just a comparison test in some sense, because if they go towards 0, then obviously A is a lot small, A sequence numbers tend to be a lot smaller than the B sequence numbers. On the other hand, if it goes to infinity, then the A sequence numbers tend to be a lot larger than the B sequence numbers. And if they approach some limit L, which is a constant, a fixed number, not 0, then they are roughly of the same size. There's only a difference is a factor of L. And then they converge or diverge together. So this is a really powerful test, comparison-wise. So we don't have to actually compare the actual numbers A and B, and we only have to look at their ratio. Does it go towards 0? Does it go towards infinity? Or does it go towards some finite number? That's actually a pretty nice way of determining this. And please note that in the cases of 2 and 3, if in case 2, if B does diverge, then it gives no information about A, and on 3, if B converges, then it gives no information about the convergence of A. So these are one-sided comparisons, these 2 and 3. Okay, moving on. Here are some examples on how to use the limits. Please study these. These are really powerful ways of determining whether a series converges. Usually the way we can compare, one place to compare always is this harmonic series. The harmonic series convergence can always be taken for granted, sorry, diverging. So the harmonic series always diverges. Also, the superharmonic series 1 over n to the anything greater than 1, you can always rely that will converge. So here are some cases you can compare these. I'm not going to go through this because we're going to need a little bit of thinking. But if you look at this, 5 to the n over 3, 3 to the n plus 2, that's definitely going to converge. You can see it immediately because you can dispense with the 2 and you get 5 over n over 3 over n. So that's 5 over 3 to the power of n. So that's going to be a series of geometric series which converges because the base number r 5 over 3 is greater than 1. So that's going to diverge no matter what. You can do it with a comparison test because the ratio of 5 over 3 to the n over 5 over 3 to the n plus 1 is going, plus 2 is going to, the ratio is going to be 1. So both converge or diverge, and because the 5 over 3 to the power of n is going to diverge, then this is going to diverge. There were some exercises here. I put some of these on this week's exercises, not many, but some, asking you to calculate the limits and use tests. Mostly I didn't put just testing exercises. I put there to check whether this converges, and if it does, determine the limit. They're pretty simple. I'm not going to ask you very hard limits, hard questions for this. You will be needing them in the future, but we have, this is a very limited course in this sense. All right. One problem with the previous tests, most of these previous tests, both the integral test and these ratio tests, is that if the sequence happens to alternate, so that there is every other is a negative one and every other is a positive one, so they can't be used because there's no limit for the ratio if it's constant, for instance, and then the changes, the sign changes. So if it alternates between 5 and -5, it doesn't have a limit. So that's going to be a little bit of a problem. So we need to discuss, this is often the case happens when we have something to the power of n and that something is negative. And then it appears, I mean, it's actually quite common in certain situations for this series to have -1 to the power of n. One situation where this might happen is when you approximate trigonometric functions, the sine or the cosine function. You take the derivative of the sine function, and what you get is the cosine function, okay? But you take the derivative of that, and you get the negative of the sine function. And you take the derivative of that, you get the negative of the cosine function, and then so forth. So when you take these derivatives, the minus plus sign will alternate. We'll see examples of this where we have to take series of higher and higher order derivatives, and then when you have this sine or cosine functions, then what happens is you end up with a series of alternating series. So an alternating series is one where the sign of the terms switches between positive and negative. Examples, -1/2 to the power of n. So you have -1/2 plus 1/4 minus 1/8 plus 1/16 and so forth. Or -1 to the power of n plus 1 over n. So you get 1 minus 1/2 plus 1/3 minus 1/4 plus and so forth and so forth. These are alternating series. And the previous examples, like using integrals or something like this, it doesn't work on these alternating series because, you know, these functions you might want to describe seldom exist. Some function that you might want to use to describe this, it just won't exist. So what can we do? Well, I'm going to skip this. This is fairly obvious. I mean, the alternating series can be, of course, thought of as you know, just this positive sequence and then -1 to the power of something in the beginning, and then you have this alternating sequence. I mean, all alternating sequences are either one form or the other, depending on whether the odd or the even number terms are positive. Okay. No need to prove this. I mean, there's a proof here, but you know, there's no need to go through this. So there are certain things that we can do with alternating tests. This is also known as the I think was known as the Leibniz condition. I think I'm not. I'll double check shortly. So an alternating series, if it's of this form where it's -1 to the power of n times some b of n, then if these numbers b of n numbers are decreasing and go towards 0, then this alternating series will always converge. So this is a far more powerful condition. I think it was called the Leibniz condition. I'll double check. I thought it would say here in this books. Yeah, it's called the Leibniz criterion, sorry, or the Leibniz test. Yeah. So you see Leibniz got a bad rap when he had this feud with Newton. Actually, originally, Leibniz's feud with Newton wasn't that bad. They were pretty cordial and on pretty friendly terms. They both kind of acknowledged each other's work. Leibniz was, you know, teaching his students. If I'm not mistaken, and I may be mistaken, there's a lot of folklore around that, and that's like, that feud is like 400 years old, so there's no way to tell what the truth is. But legend has it that that they were pretty cordial about all this invention of differential and integral calculus. Both thought that they had been the real inventors, and Newton acknowledged that, yeah, maybe you did, maybe you didn't. He was like, you know, probably you're a stand-up guy and probably didn't, you know, steal this thing from me. And Leibniz said, yeah, no, I didn't, bro, and so forth. But then it kind of heated up over years after that, when Leibniz was teaching his students this calculus, and his students kind of took it up, so that, you know, this Leibniz stuff is so much better. He's so much better than Newton's calculus, and you know, that kind of escalated rapidly at some point, and then, you know, just there was kind of a appeal to the Royal Society, but Newton was like, you know, man, I am the Royal Society, so, you know, I'll banish you from this whole thing. And you know, it really got ugly in the end, but it wasn't so in the beginning. And, you know, Leibniz got a bit of a bad rap from that, but his name lives on, and he did a lot of cool stuff. Like he figured out that these series, alternating series, as long as the terms converge to zero, you know, the sequence of terms approaches zero, and at least from some point onwards, this alternating sequence is decreasing. Then, yeah, it will converge, and it's really powerful. So, for instance, this 1 over n series doesn't converge, but if you have minus 1 to the power of n over n, that does converge by the Leibniz criterion. And this they call it alternating series test. I don't know. These are they're still, I mean, 400 years afterwards, they're still, you know, playing on this Newton's feud, maybe. I don't know. I'm used to calling this the Leibniz criterion, but, you know, whatever. Alternating series test. So here are some converging series. Obviously, 1 over n squared. I mean, it's obvious. You know, if it's alternating, it's going to 1 over n squared goes towards 0. Minus 1 to the power of n plus 1 over n squared obviously goes to 0. But, you know, B, the criterion doesn't work there. You have n over n plus 1. Well, the terms are decreasing, but they do not approach 0. Look, n over n plus 1. That's a term that goes towards 1, actually, as n goes to infinity. So that's not going to converge. So here's a task for you. Determine whether this series, minus 1 to the power of n plus 1 times n over 2 to the n, converges or diverges. And, you know, I'm just going to give you 3 minutes to discuss this. I mean, it's so simple. Check it out. 5.18, discuss, 3 minutes. So, whether this converges or diverges, fairly simple. Fairly simple, I mean, n over 2 to the n obviously goes towards 0. This is an alternating series, and so it's going to be convergent. Fairly simple. So here's a talk about the remainder of the alternating series. So if you have an alternating series, then once we hit the part where the terms are strictly decreasing, then we know that the remainder, you know, if you take a partial sum up to some capital N, then what remains is at most the next term that was left out. I mean, it cannot be bigger because you're going to be subtracting something from that. It's very easy to see because these are decreasing. So you have the n plus 1th term. The next one is going to subtract from that, but it's going to be smaller. So there's going to be a positive remainder. Then you're going to add something, but it's going to be smaller than the one that you removed, and so forth. So whatever is going to be added and removed, it will never contribute as much as the last term that was left out. So for instance, if you have the alternating series of where you are adding -1 to the power of n over n, then if you cut that short to the term capital N, you know, the first n terms, the series, you add those up. The last one you leave out is 1 over n plus 1, and let's say that has a positive sign. So the rest of the sequence is at most 1 plus, rest of the series contributes to the sum at most 1 over n plus 1. So that's actually a powerful tool, right? So here are some ways of estimating those. I'm not going to go there. I'm not going to ask this remainder so much. So, you know, sometimes if you're doing physics, if you're a physicist or you're doing some other calculations, it's not uncommon. Why would we want these remainders? Well, why would we want them is because very often the case is that we come up with a model of a mathematical model of some behavior of some system or you know, some variable, and we determine that the effect of all things combined comes down to an infinite series. So we add this stuff and it's a convergent series, but still. And then when we are dealing with that, we're going to leave out a lot of those terms. One place where this invariably happens is acoustics. So when you're dealing with a model that models the acoustics of some system. So let's say you're blasting a room with certain frequency of sound. Well, what happens is that there will be reflections of that sound, and there will be what we know harmonics. I don't know why they're called harmonics, because it's really geometrics, right? The series is actually not a harmonic series. So you have, well, you know, in some sense, yes. I mean, you will have, it's actually harmonics. Yeah, that's true, actually. It is harmonics, because you have that frequency. Let's say you're blasting it with 100 hertz. And then you got reflections and you have interferences, then you get 200 hertz, 300 hertz, 400. So the sum of 1 over k times, and then there is a coefficient. Let's say the attenuating factor for these higher frequencies let's say it's inverse square law. So the higher the frequency, you know, it's proportionate to the inverse of the square of the frequency. So you get this 1 over k squared kind of amplitudes for those higher frequencies. And then, you know, you are looking for the energy that is energy that is reflected from the walls, let's say, of the room that you're blasting with this 100 hertz, very low bass sound. You can hardly hear it. It's very, so the noise, the walls start resonating, and it causes this higher frequencies to appear. You can hear these this sound then because of the resonance. So that's where you have you can write a power series or a series of different frequencies that are going to be appearing, and then you approximate the energy. Well, you want most of the energy, but you don't want all of it. So you're going to leave that. You're going to take, let's say, 5 terms from the beginning of that infinite series and leave the rest. And you want to approximate how much energy are you not taking into account. And that's why you may need these remainders. Not sure if the alternating series ever appears in there, because the energy is usually positive, but you know, you get my drift. So very often when you have a model of something, then what appears are these infinite series, and you want to approximate. And in physics and several other kinds of modeling, you only take the first couple of terms of that series and then leave the rest out. And then if you can prove something about how much of some quantity that you are dealing with, be it energy, be it voltage, be it whatever, is left out because of you only taking a couple of terms from that series, then you should be good, because you know that, okay, my error is at most this much. This is a very powerful tool, but we don't have the scope to, I don't want you guys to be having to learn. Well, I would like you to learn, of course, but I don't want, I'm worried that you will spend too much time on this and not the core material. Well, one thing about the alternating sequence, or alternating series, is that we can look at what is called absolute convergence. Absolute convergence means that instead of looking at the A sequence or the B sequence that we're dealing, we can look at the A series, we can look at the series over the absolute value of AN. And obviously, well, it's not necessarily obvious, but similarly to the integrals and so forth, if we can say that this absolute convergence happens, it means that even if we take the absolute value of A of n and then add those, then that converges. Well, that's very powerful convergence. It converges very rapidly. Then there is what is called the conditional convergence, and that is that A of n series converges, but only because it's alternating, or, you know, there are negatives in there. And if you take the absolute value there, then it diverges. Then that's called conditional convergence. So absolute convergence means that it converges whether or not there is this changes in the sign, and conditional convergence means that it only converges because the sign of the term is changing, because it's alternating. So for instance, a harmonic series does not exhibit absolute convergence. A harmonic series is conditionally convergent. Sorry, the alternating harmonic sequence, sorry. And whenever there's absolute convergence, obviously it converges, but conditional convergence is less obvious. So one way to prove that a series converges is to prove that it converges absolutely. If it converges absolutely, then there is no need to do the Leibniz test or anything like that. Here's a proof, but I don't know why you would want to prove this, because obviously, you know, if you add these up, then adding these up will converge. I mean, this is smaller than, all subsums of this are smaller than or equal to all subsums of that. So no need to worry about that. Here are examples of absolute versus conditional convergences. Let's see, the first one, -1 to the power of n plus 1 over 3n plus 1. We can use the Leibniz criterion, or the alternating test. We see that 1 over 3n plus 1 goes towards 0 as n goes to infinity. This is an alternating sequence, so it's going to converge. But if we take absolute convergence, if we take the absolute value and we can use, let's say, the limit comparison test, we notice that the limit of 1 over 3n plus 1 divided by 1 over n, so we're comparing it to the harmonic series, is 1 over 3. So because the harmonic series diverges, then this diverges. So this series converges, but not absolutely. So it's a conditional convergence in this sense. So in B, there's absolute convergence because the cosine function there may be changing signs, but really, even if we replace that by 1 over n squared, we'd get the superharmonic series, and yeah, it would be convergent. Fairly simple. again, I'm not going to do this 520. Determine whether the series converges absolutely, conditionally, or it diverges. Let's look at the terms. It's an alternating sequence. We have n over 2n to the 3 plus 1. Okay. There we can use, let's say, comparison. N over 2n to the 3 plus 1 is smaller than or equal to 1 over n squared, because if we just take the 2n to the 3 plus 1, so 1 over 1 half times 1 over n squared. So we can, I'll just write it into the chat window. So n over 2n to the 3 plus 1 is smaller than n over 2n to the 3, which is 1 half times 1 over n squared. And we already know that this well, if we take this term, it's going to be 1 half times the sum of 1 over n squared, and that's going to converge, so it's going to converge absolutely. And again, it's an alternating sequence, then obviously it converges, but it converges absolutely as well. There is a discussion here about the absolute and conditional convergence differences, because the thing about these conditional convergence is that, in fact, if you take a harmonic series, which is the alternating harmonic series, so it's a harmonic series but with the sign switching, we can arrange the terms into this series where the new series diverges. For instance, we take all the positive numbers, we add them first, and then we take the negative numbers and then second. These go towards infinity. So it has a subsequence that does not converge, a subseries, a subsum. So we need the negatives to balance out the positives. If we try to rearrange them in an infinite way, then we get two diverging sequences. So you can say that the absolute convergence means that it doesn't matter how you rearrange these terms, it will converge. But conditional convergence means that you have to add them in a certain way to keep them from blowing up to infinity. So the alternating harmonic series convergence is conditional on it being calculated in a certain order. I'm not going to go through these examples. I urge you to look at that, but we are pressed for time, sadly. So, yeah. Okay. Sometimes we don't get, so sometimes we get series that are not so easy to determine whether they converge. So here are three things that we will learn, three more things that we learn, the so-called ratio and root tests. So we want to be able to check the ratio test or the root test to determine the convergence of a series. So the thing is, the ratio test simply looks at a comparison to, this can be, the ratio test can be thought of as a comparison to the general geometric series. So remember that in the general geometric series, we had this sum as n is from 1 to infinity. Sorry. We had a times r to the n. Let's say this is my, it could range from 0, it could range from 1, but let's say this from r to n. So we know that this converges we know that this converges if and only if this this R is smaller than 1. And if we take this and we look at the consecutive terms, so the ratio of consecutive terms, we have a r to the n divided by a r to the, sorry, a r to the n plus 1 divided by a r to the n. So this is the ratio. So it's r, right? So the ratio is r, and if this r is smaller than 1 in absolute value, then obviously this is going to converge. And then we can kind of compare this in general. This may not be, this AN series may not be a geometric series per se, but when we do kind of a comparison, how does it compare with a generic geometric series? What would, if we take something that would be like a geometric series, what would the ratio of these elements be? And we look at the ratio between successive elements, or successive terms, an plus 1 and an. And if this ratio is smaller than 1, then this will be like a rapidly diminishing, not rapidly diminishing, but like a geometric series with the base number is smaller than 1. It will be thereabouts. From certain point onwards, it will be pretty closely approximated by the geometric series. If this is so, then it converges absolutely. Obviously, if this ratio is greater than 1, then what happens? If it's greater than 1, then the successive elements tend to get larger and larger. So it's definitely not going to converge. It's going to diverge because, you know, the next one is a teensy bit bigger than the previous one, and you know, they won't approach 0. This getting a ratio greater than 1 is tantamount to getting the divergence test, where we look at the limit of these elements per se, these terms, A and terms, if they don't go to 0. They won't go to 0 if if this ratio is greater than 1. In fact, they will go to infinity if this ratio is greater than 1. If it's equal to 1, if this ratio is equal to 1, we just don't know. We won't be able to tell. See, let's take the superharmonic series. We have n plus 1 to the 2 over n squared, right? So this is n squared plus 2n plus 1 over n squared. And this is going to be 1 plus 2 over n plus 1 over n squared, right? And limit is 1. I mean, as n goes to infinity, then that's limit is 1. So the superharmonic series does converge, but then the harmonic series, where we have n plus 1 over n, well, that is equal to 1 plus 1 over n. And again, limit is 1. So we see that there are both, when we get this ratio of 1, then this is an inconclusive test. Because for that limit equal to 1, there will be both convergent and divergent series. But if the limit is between 0 and 1, then it is going to be a converging sequence if it's smaller than or equal to 1. Sorry, smaller than 1. Smaller than 1. So this gives partial information. It doesn't always give you information. There are plenty of these tests fail to give you a clear-cut answer. Does it converge? This may fairly often. This gives you that the ratio is 1 and it doesn't provide with information. But if it's less than 1, then it's going to be pretty good, right? So think of the ratio test as a comparison to a geometric series. All right? That's a ratio test. Then there is something, you can look at this proof that this works. It's fairly obvious that you can then approximate it with something that is, a little bit of an algebra here, but. And what is more, by the way, is that you get absolute convergence if this is 0, if this is smaller than 1. It's absolute convergence. It's not even conditional convergence. It's absolute convergence. And the thing is, if it's a conditionally convergent but not absolutely convergent series, then in fact this ratio test probably gives you an inconclusive result. Well, it will give you an inconclusive result. So how do you use this ratio test? Here are some examples. 2 to the n over n factorial. Using the ratio test, you get that the limit is 2 to the n plus 1, blah, blah, blah. You do that, and you notice that the limit is 2 over n plus 1, which is 0. And so this is a convergent, absolutely convergent series. The second one, I'm going to skip that because that's in a home, that part of that is in the homework. So I would like you to do that, but not yet. So let's see, n to the 3 over 3 to the n. Use the ratio test there. Again, I'm giving you 5 minutes as a group to do 5.21, discuss this. I'm going to just recreate these rooms because apparently there's a discrepancy. Some people have left, so you have now new rooms. So go through this 5.21. I'll give you 5 minutes and we continue then. I hope you were able to determine this. Just as an exercise, so for the ratio test, in this case, you have n plus 1 to the power of 3 over 3 to the power of n plus 1. And then that divided by n to the power of 3 over 3 to the power of n. And then you can find out that this becomes a, well, you can write this n to the 3 plus 3n squared plus 3n plus 1 over 3n to the 3. Which, I mean, if you look at the limit, is equal to 1 over 3. So conclusion converges. I mean, you get the limit is 1 over 3, so yeah, that's it. Similar to this idea is what we know as the root test. So the root test is the ratio test was easy to justify using the idea of the geometric series. For the root test, it's not quite as easy to justify. You can think of this as we have 1 over n to the power of something, and we're actually looking at something from there, but it's a little bit trickier than that. So so the idea here is that we take the limit of the nth root of the nth term, and so if this happens, if we have a limit there, then it means that for sufficiently large n, the nth term will be roughly equal to this root limit to the power of capital N. I mean, if you think about it. So if we take that n is roughly, I'm using p here because I don't get the p to the capital N. Then if we take the root, nth root n is roughly equal to p, right? And now if this root test gives us this limit rho, and it just happens that the rho is smaller than 1, then this will converge, absolutely. If it's 1, it's inconclusive because, you know, 1 to the power of n. I mean, what do we know? I mean, if it approaches 1 and then to the power of n, and we don't know. I mean, which one does it go towards 1 faster? Does the exponent go up fast enough to offset the growth, right? So this is again one of the situations where this this compares it roughly to the geometric series up from some point onwards, and if we have this base number rho is 1, then we are inconclusive because we can't really say anything. So the root test is fairly similar to the ratio test, and more often than not, you know, if it's hard to determine whether it's going to converge, then this might give you just equal to 1 as well. So here's a one where you can use the root test, where the ratio test is a bit harder maybe to do. You have polynomials on both the numerator and denominator, and then you have that to the power of n. And that's going to be a little bit tricky, but it's easier to do the root test than it is to do the ratio test, for instance. And if we do the root test, we notice that this terms will go towards 1/4, and it's going to be a convergence series. On the other hand, if you take b, n over the logarithm of n, that's going to go to infinity, and you know, you're not going to get convergence there. So it's going to diverge. So now we have several different convergence tests, and that's really, you know, now we're there. This was the last one, so we're here. So how to test for its convergence of a series? If none of the tools that are provided here work, then you're off the hook. If you cannot do it with any of the tests that are provided this far, then you're off the hook. I'm not going to ask anything that cannot be determined by these tests. Firstly, memory. Is it a familiar series? If it's a harmonic series, it diverges. Is it an alternating harmonic series? It converges. Is it a P series, a geometric series? Check the power of P and so forth. These converge or diverge, we know them. So this is just look it up from the table or remember. Alternating series. If not, go forward. Can you find a similarity to a P series or a geometric series? If so, comparison or limit comparison. Do the terms series contain factorials or powers? Try the root test. If not, if there are no factorials or no powers, try the ratio test. And then, you know, use the divergence test. If you can't get any, try if you can find the integral. If none of these work, then you're off the hook, right? But I guarantee you, if it diverges, one of these will catch the divergence, if it converges, one of these will catch the convergence and you will be able to solve it with these tools, because I will not put you against series that do not conform to this. There are series obviously that don't conform, you know, that you cannot solve with this, but all the ones that we're going to have here are going to work. So basically that's it. And this was the last material really that is new material. There's a lot of step-by-step instructions on how to do these and please go through them. I'm not going to go through them now. We're going to discuss these during the exercises a little bit. So starting Thursday, before then, go through these examples and look at them. And there was also a table here. Don't have to learn this by heart, because when you're doing the exam, you can consult this test, this sheet. But the thing is, focus on trying to understand why they work. I tried to give you an idea of why each of these tests works and why they don't why or how they work. I mean, the only one that I didn't really couldn't give you a very nice lay down on was really the Leibniz criterion. So that you just have to trust. If it's an alternating series, then the Leibniz criterion here. But remember, it only applies for the alternating series. And that's it. That's it. I mean, no more tests, no more nothing. I'm going to mention one more thing before we stop. I'm going to mention one more thing that we really kind of like walked over a little bit. And of that, I'm sorry, but you know, we'll talk about that a little bit. Oh, sorry, it was in volume 1. It wasn't in volume 2. Sorry. Let's take the volume 1 here. So there was one thing that we skipped, maybe in a bit of post haste. That was the where was that? Yeah, limits at infinity. So the limit at infinity, they didn't talk about that a lot, but the limit at infinity was simply meant can be simply thought as a somewhat differently. So the limit at infinity of, as x goes to infinity, f of x is L. If, you know, we can say that if for any epsilon, I mean, this is just informal. Let's look at the formal definition. There has to be a formal definition here somewhere. Yeah, here. So that if you choose the epsilon, then if you choose n great enough, large enough, then for all x greater than n, the f of x will be closer than epsilon to that limit. So this is fairly simple. So we didn't discuss this all that much. I just kind of like took it for granted that you know. And of that, I'm sorry. I waltzed over this a little bit in haste. We had a little bit of a, let's say, well, this book wasn't familiar to me, and I was, I skipped that part because I thought that I had already discussed it, and I realized later that no, we skipped this, and I'm really terribly sorry about that. So if we're looking at infinity, you're going to be needing this if you use the integral test. We didn't actually do this limit at infinity in anywhere else, except the integral test is where you need this. So when you do the integral test and you get some number, some function f of x out of that integral, and then you have to look at what happens to that function at infinity, because that's the criterion you compare against in that integral test. So really, the limit at infinity is L. If we can find this for every epsilon, we can find the limit so that if x is greater than that limit n, then f of x is closer than epsilon to L. So here are some examples, like for instance, polynomials go to infinity, power functions, and then, you know, all that. But then there was these situations where, for instance, 3x squared plus 2x and so forth, you can subtract, or, you know, how do you call that, simplify this, and you get 0 eventually. There are several examples here. If this was not familiar to you, I'm not going to ask. This is the only place you're going to be needing this is the integral test. And I can promise you that in the integral test, the only kind of functions that you really need are something like 1 over n, 1 over x, and then, you know, x or something. You have to recognize that the logarithm of x goes towards infinity if x goes to infinity. But for the polynomials, you know, if it's x to the minus something, that goes to 0. If it's x to the plus something, that goes to infinity if x goes to infinity. That's all. That's really all there is to it. So if you want to check this out, please feel free. But I'm not going to ask very many questions that where you require this. So you can just as well consult some table of or something about whether this is going to be convergent or divergent, you know, if you go to infinity, and how to find these limits. Rational functions and logarithms, that's all we are actually going to be dealing with. Okay, exponential function, if you have a to the power of x, then as x goes to infinity, then that goes to 0 if x is smaller than 1, and if x is, a is smaller than 1, if a is greater than 1, then that goes to infinity. And if it's 1, well, then it's 1. Okay, that's the only thing really that we skipped, which I'm really terribly sorry about, but I hope that you will be able to look at this by yourself. I can put some extra material and rehearsal material for you later this week. So I'm going to stop the recording, and we're going to still have the lecture on Friday. On Friday, I'm going to go through the learning objectives and all the topics and all the ideas that we discussed one by one, very quickly. Tell you what to expect from the exam, and tell you a little bit about the grading. And then I will also, I hope to get some feedback or discussion from you. But at this point, I'm going to stop this recording.